Okay, so in case you're just really stuck on how to get started here, write down your givens first and break this thing up into part 1, part 2, and your totals. Okay, so jetliner travels with a speed of 350 kilometers per hour east. That should actually say not speed, but 350 kilometers per hour east. That's not a speed, that's velocity. Yeah. Okay, so I'm just going to write part 1. I'm going to write V with the arrow over top for velocity. Okay, 350 kilometers per hour. And I'm going to put an E after that for east. And I'm going to put in the time. 45 minutes is 0.75 hours. Okay, that's all I know for part 1. Okay, in part 2, okay, it's traveling west at 375 kilometers per hour. Okay, so V is 375 kilometers per hour west. Okay, and it does that for 30 minutes, 0.5 hours. Okay, now it wants the total displacement. Okay, so what I'm going to do here is I'm just going to put totals and averages as my last column here, because this is where I need to calculate things. Okay, they want the total displacement. Okay, let's do that first. Do I have the displacement for any of the parts of this trip? But can I find them? I can. Okay, so it's going to be the same calculation, so luckily I only have to do algebra once here. Okay, but if I want to find D, I have to use this formula. V equals D over T. And I just have to manipulate and solve for D. So if I want to get D by itself, what do I do with T? Multiply it over to the other side. Okay, boom, now I've got my formula, and we're going to use it again over here because I'm calculating the same thing. All right, so D is going to equal 0.75, okay, times 350. Okay, so 375, or sorry, 350, not 375, that's the next one. 350 times 0.75. All right, so that plane, since it's flying, it would go 350 kilometers if it went for an hour. It only goes for 3/4 of an hour, so it only goes 262.5 meters. Okay, so I write that down. I've got the D now for the first part. Okay, I need to also get D for the second part. Luckily, I have the same pieces of information, so I don't have to do my algebra twice. I can just write in here, it'll be V times T, and go 375 times 0.5. Okay, what did I not put on this displacement that it's supposed to have over here? Is displacement scalar or vector? It's vector. What do I not have on it? Wait. Yeah, I don't have a direction. Degrees is sometimes a direction. Okay, in this case, I was flying east, so I must be displaced east. That's going to be important in a minute. Okay, so I'm going to do this calculation, 375 times 0.5. Okay, so 187.5. Sorry, that's not meters, that's kilometers. Okay, 187.5 kilometers. West. Okay, this plane backtracks on itself. First it flies east, then it flies back the other way. All right, so if I want to find the total displacement, I just have to add together the two parts that I have. But one of them needs to be negative, exactly. Okay, so what we usually do with compass directions is we treat it just like what you would have learned in math. okay, with an XY plot. This would be the positive Y, this would be the positive X, negative Y, and negative X, okay? On a compass rose, that's north, east, south, and west. So east naturally becomes positive, north becomes positive, south and west become negative. All right, so I'm going to write in here my 262.5 kilometers, okay, and that was east, okay, plus 187.5 kilometers west. All right, when I do that in my calculator, that looks like this: 262.5, okay, minus, okay, or I could go plus negative, doesn't really, let's do that, plus negative, okay, 187.5. Okay, so the total displacement of this plane is 75 meters, and it came out positive. And positive is which direction? East. Okay, so, I mean, that makes sense, right? It flew 262.5 kilometers east, and then it only went 187 west, so it didn't get all the way back. Its displacement is, it's still east of where it started. Does everyone follow me there? Okay. Okay, that's the first part. What's the total displacement of the plane? 75 kilometers east. Okay, did I have to do a little bit of work to get that? Absolutely I did. But I'd have had to do that work to do the next part. Okay, so for I did part B first instead of part A. Sorry. What's the distance traveled? Is distance scalar or vector? Scalar. So does it care that one's east and one's west? Okay. It's just how far did the plane fly in total. So what do I do with this number and this number? I just add them, and I don't make one of them negative. Okay? This is just about how far I'm going. Okay? So to get the distance, which is never going to get smaller, it's only ever going to get bigger, okay, is just 262.5 plus 187.5. Okay, so its total distance traveled is 450 kilometers. No direction on that because it actually turns around. So, okay, that's a scalar quantity, doesn't get a direction. Okay, is everybody with me there for part A and part B? Okay, that's just I've got to recognize whether I'm calculating a scalar quantity and I'm just adding things with no consideration of direction, or I'm finding a vector quantity where I do have to consider direction. Okay? Then I've got to make one thing positive and one thing negative. In Science 10, it will never be more complicated than that. Okay? There's never going to be trigonometry where it's like 10 degrees south of east. Okay? So we won't have to do any of that. It'll be up and down, right and left, north and south. Okay? It'll always be positive and negative. We call that one-dimensional vectors. Okay? All right, for part C, plane's average speed. Is speed vector or scalar? It's scalar. This you have to memorize, okay? That part you have to memorize. All right, so speed is distance divided by time. In fact, they want the average speed, so that's the total distance divided by the total time. Did I just calculate the total distance? I did. Okay, so that part's already done. I can just plug this number, 450 kilometers, on the top. Have I calculated the total time yet? I have the times, but I haven't calculated the total time yet. What do I do with those two times? Add them together, exactly. Okay, so 0.75 hours and 0.5 hours is 1.25 hours. Okay, pretty simple calculation then. Okay, take that number I just calculated and divide it by 1.25. Okay, so the plane's average speed is 360 kilometers per hour. Okay, everybody all right with that? All right. Are we doing any really complex stuff, or have we used the same formula like 6 times already? Right, have we just used v equals d over t again and again and again in this problem? Okay, and that'll happen sometimes. Sometimes you'll get a problem where it's not just one calculation. You might have to use v equals d over t a couple of times. All right, last part. Oh, no, I didn't ask for the average velocity, did it? Could we calculate the average velocity? We've already done all the work for it, really. Okay, we could totally calculate the average velocity even though it's not asking for it. Okay, average velocity would be our total displacement divided by our total time. I already have all of those numbers. All I have to do is punch them into my calculator. Okay, my total displacement was 75 kilometers east. Okay, total time is still 1.25 hours. That doesn't change. Okay, is my velocity a lot slower? It is, because it's dealing with a much smaller distance, okay, or in this case, displacement. Okay, it's only dealing with how far from where it started it ended up, not how far it actually went. Okay, average velocity is always going to be smaller than, and in rare cases equal to, speed, but it'll never be bigger. Okay, because we're almost always dealing with a smaller amount. Okay, think of it this way: what's the shortest route between 2 points? Any 2 points. Straightest route is a? Don't overthink it. You all know the answer. The shortest path between any 2 points is a straight line. That's what displacement is. Displacement is always the straight line, magnitude and direction from start to finish. That's why it's always going to be smaller than or equal to the distance. Okay? In that question we did about the Walmart, the trip to Walmart, okay, remember we had like our house, this was our starting point, okay, this was our ending point, and we did this. Okay? That was our distance. That's how far we actually had to go to get there. Okay? But this was our displacement. Okay? We couldn't walk that way. There's stuff in the way. Right? But that would be the shortest path. You just can't always take it. But when a question asks you about it, you can still calculate what it would be, even if it would have been impossible to actually do it. Everybody all right with that? Now, if I had a helicopter, I could totally do that. Okay? Making sense? All right. That's as tricky as they'll get. A question like that's as tricky as they'll get. Okay? You won't get ones harder than that. And incidentally, that kind of stuff will be on Friday's quiz. Okay? If you haven't tried to practice quizzes, not a bad idea to do that. Okay, were there any questions from the worksheet you did with Mr. Pumphrey yesterday? Pretty straightforward stuff. We might spend a little bit more time on that, but probably not a lot. Okay, we got to get through some graphing stuff this week.
On Friday on the quiz, will there be questions where you have to convert things to the metric system?
Possibly, but I'll remind you. Okay, I'll point it out and say, hey, make sure your units match here. Now, I do expect that by the time you get to grade 10, you can do the metric system. Good news, on your periodic table and up here on the board, there's a metric conversion chart. Unless you lost yours and grabbed an old periodic table, then you might not have it. But your periodic table should have that chart right there on it, okay, to help you with metric conversion. Now, I'm never going to ask you to do a crazy metric conversion like, you know, you have X many picometers and you need to convert it to kilometers, like meters to kilometers. Okay, that's what I'm going to ask for. Okay, guys, kilo always means how many? Okay, if you have 100K, how much do you have? Someone said, hey, I'm going to pay you 100K for that. How much are they going to pay you? $100,000. What does K stand for? 1,000. Kilometers, 1,000 meters. Kilograms, 1,000 grams. Okay, that's the beauty of the metric system. K always stands for 1,000 tons. Okay, that's why the metric system is so much better than the imperial system. Okay, you can remember deca means 10, hecta means 100, kilo means 1,000. Okay, if you have deci, that's 1/10, centi, 1,000 or 100, milli, 1,000. Okay, they always mean the same thing. It doesn't matter whether it's grams, meters, liters, bytes. Okay, the metric system treats everything the same. So you don't have to remember things like there are 12 inches in a foot, 3 feet in a yard. Okay, 5,280 feet in a mile. Like you have to remember all these, there's 16 ounces in a pound. You have to remember all these weird numbers in the imperial system. In the metric system, the numbers are always going to be factors bigger, 10, 100, 1,000, always. Okay, so yes, you will have to know how to convert hours to seconds, okay, minutes to hours, minutes to seconds. Okay, that stuff I do expect you to be able to do. Okay, everybody come up and grab a Chromebook. All right, so we're just going to talk quickly here about kind of the purpose of graphing and the format that your graph should always be in or should appear in. Okay, so right now I'm looking at this graph here. Okay, I know very little about the effect of temperature on the rate of photosynthesis. Okay, and I teach, I used to teach just biology, believe it or not. Okay. And I still know very little about the effect of temperature on the biochemical process that initiates photosynthesis. Okay, but can I look at this graph and get a pretty good idea of what that relationship is? Right? Without having to read a whole bunch of background, can I look at this graph and know that generally, as temperature goes up, photosynthesis increases until it gets to about 35 degrees or so, and then just falls off and quits. Okay? Just looking at that graph, I know that. Is a graph a concise way to convey data that may have taken a long time to acquire and would have taken a long time for you to read about? That's the purpose of a graph. Okay? It's why graphs are one of the visuals you see all the time. You see it on your weather app on your phone. Okay? You see it on TV when they're, on the news when they're telling you so-and-so's popularity is doing this and so-and-so's stock prices are doing this. Graphs are always used because they convey that information very quickly. You can see the trend, you can recognize what's going on without having to listen to some guy that sounds like Ben Stein drone on, okay, for an hour about all the minutia of all of that. Okay? You can look at it and go, that guy's really fallen off. Okay, or oh, I got to buy those stocks because they seem to be going way up, unless they're Tesla stocks, and you probably want to stay away from them. Okay, but yeah, those kind of things that you can read pretty quickly. But if you saw a graph of Tesla stocks over the last little while, you would go, I don't want any part of that. So I'll just lose money. Okay, so that makes sense. Graphs are important, right? They tell us lots of stuff, but they tell us it quickly. Okay, now on this graph, this is a pretty good graph. I would not give this graph 100%. It has one mistake on it. Okay? Does it have a title? Okay. Is the title important? Without that title, am I going to have a pretty hard time telling what this graph is about? Yeah. Okay. It's got the points on it. It doesn't make great use of the space. I wouldn't take a mark away for that, but it doesn't make great use of the space. The scale should probably be a little smaller, so the graph, the actual data could be a little bigger. Okay, on the x-axis here, we've got a label. It tells me that temperature was the manipulated variable in this experiment. That's an important thing for you to know. The manipulated variable always goes on the x-axis. You should probably write that down somewhere. Okay, the manipulated variable is always on the x-axis. So which variable probably always goes on the y-axis? The responding variable. That's what you're trying to see, right? Now, temperature is not a super common manipulated variable. The most common manipulated variable is time. Okay? But in this case, this was an experiment about temperature versus rate of photosynthesis. Okay? So it clearly shows that as the experimenter increased the temperature of the experiment, that the rate at which photosynthesis occurred went up and then plummeted. Right? So we can see the effect of the manipulated variable on the responding variable. It's a great setup. Okay? Graphs aren't always as simple as this. Graphs can sometimes do this. Okay? Okay, a graph can be set up in quadrants. We don't do that very much, but okay, sometimes it can be set up in quadrants, and it can start in the negatives and come to the positives. More often than not, what we'll have in this course will be graphs that look either like this one or like this. Okay, and we would have like, here's a time of 0, here's a time of 30 seconds, and you'd have all your intervals in between. Okay, and we might have, you know, something like this. Okay, maybe this would be like the position in meters, and this would be the time in seconds, right? Okay, what that's telling me is the object was forward and then it was backward, okay, because it went down into the negative. So this would actually be a graph of about an object standing still at this position, okay, and then walking backwards, okay, and ending up over here. Okay, the 0 position would be directly in front of Juliana. Okay, I started over there by my desk, and I walked backwards to here. Okay, that's what that graph would be showing. That's about as complex as we'll get. All right, so this graph's got a good x-axis, it's got a label, and it's also got the units. Okay, it's important to say this is degrees Celsius, or I might mistake it for degrees Fahrenheit, in which case this whole experiment occurred below freezing. That's obviously not true, so they had to tell me this is degrees Celsius. Yeah. Okay, because that makes a huge difference. Units are really, really important on a graph. Labels and units. So, what's missing from the y-axis? There are no units. I don't know what their measure of the rate of photosynthesis was. Okay, I would imagine the ways to measure the rate of photosynthesis would probably be measuring the milligrams of oxygen that would be produced by the plant over a period of time. Okay, I don't know exactly how they would do that, but that could be one indicator. Maybe they would measure somehow, maybe well, it says rate of photosynthesis. I don't know what that would be in milligrams per hour. I don't know. That's kind of misleading. That graph suddenly tells me a little less about what was happening in that experiment. I can see that the rate goes up, but I have no idea how they measured that rate. And that's an important thing to know. Okay? So what I expect on any graph you build me is a title, okay? It's clear and concise. Okay? I expect each axis to have a label with units. All right? And then I would expect your points obviously to be plotted, okay? And if necessary, and I'm going to show you all how to do this today, a line of best fit with an equation for it. Okay? But a graph has to have those things to be considered correct and properly communicative. Okay. All right, so on your Google Sheet, one of the Google Sheets says it's a graph of the number of sheets versus thickness. Okay, so if we go, it's not, okay, so book thickness. Okay, see this tab right here on your Google Sheet? It says book thickness. Okay, let's go there. All right, so in this study, it's not really an experiment, but in this study, okay, somebody wanted to see how thick basically a book would be based on how many pages it had. All right, so that made pages the manipulated variable. Thickness responds to that. Okay, the more pages a book has, the thicker it's going to be. Everybody okay with that idea? Okay, so which axis should number of sheets go on? It should go on the x-axis. It's the manipulated variable. Books get thicker with more pages or more sheets. All right, so follow along here. We're going to build a basic line graph of book thickness and number of pages or sheets. Okay, so what you want to do is put your cursor, okay, just kind of click out here somewhere just so the box comes out here, and then click and drag. You want to click in sheet or in cell A1, okay, so where it says number of sheets, click and drag so that it highlights all of the data. You see how it's a lighter color blue for me? Should be a lighter color blue for you. Okay, and then it'll draw a box around all of that. Okay, then we're going to go to Insert, and you'll get your drop-down menu. All right, you're going to click Chart. Okay, so we've highlighted, we've clicked Insert, and now we want to click Chart. Okay, so right here. All right, sometimes Google Sheets picks the right kind of graph, sometimes it doesn't. Okay, sometimes it'll pick a bar graph or like just weird stuff that we don't want. Okay, this is exactly what we wanted. We wanted a scatter plot. That's what this is. So scattered dots along the graph. Okay, am I going too fast? Okay, because if I'm going too fast, just let me know. Okay, so right now is most of the stuff that we need on this graph that we just talked about. Does it have a title? Yeah, and sometimes, you know, if you pick these right, it'll give you a pretty good title. Okay, it also says thickness in millimeters on the y-axis, so it's got a label in units, and it says number of sheets on the x. Okay, is that okay for the label and units? It is, because in this case, number is the units, right? There's no, I mean, we could say sheets in brackets or pages in brackets if we wanted to, okay? But it says number of sheets, so it kind of just says, there's no units here, it's just a number, right? It's kind of a scalar quantity. Okay, now, graph looks pretty good, but we need a couple of other things on this graph, okay? We need to put on what's called a line of best fit. All right, how many people have heard that term before? Best fit line, line of best fit, linear function. Okay, you guys done graphing and math yet? Yeah, okay. All right, so here's what we're going to do. We're going to click on the three dots here on the top. You may already still have this. Just click Edit Chart. You probably still have the chart thing here. Okay, we don't need to change anything on the setup. It's set up perfectly, so we didn't need to do anything. But we do need to customize our graph a little bit. So we're going to click on Customize. Okay, the chart style, that's fine. Okay, when you click on that, you can see there's just a few things if you wanted to, play around with how it looked, you could change those, but we really don't ever do anything in there. Chart axis and titles, we've already decided those were good, but if we did need to change anything, okay, if we wanted to change the horizontal axis title, okay, we could change it and just type in here something else, like it says number of sheets, and then I could go / pages if I wanted to. And it would change it. If we needed to change something or add something, that's how we would do it. Okay, if we wanted to go to the vertical, we just click on that arrow and it would change it over to the vertical, and we could change the vertical one. It says thickness in millimeters. That's fine. Okay, this is the one where we're gonna probably do the most changing around in the series menu. Okay, so just click on the drop down there for series, and there's quite a bit of stuff in here. All right, so it says, do you want to use blue dots? Yeah, we're fine with blue dots. If you want to change it, that's fine. Okay, you can make them thicker or smaller. That's totally up to you. I sometimes do make them smaller on certain kinds of graphs. Okay, point size, so like 7 pixels. I sometimes make it like 2 pixels. You can see that just changes the size of the dots. It's easier to see if they're actually on the line or not when they're smaller. Okay, speaking of the line, all right. We don't have one yet. So if we keep scrolling down, and that's what I did here, right? I just grabbed the scroll bar, okay, and I scrolled basically down to the bottom of that menu. I've got 3 check boxes there. Okay? One of them says trend line. Check that box. Okay? Now it's drawn a line of best fit for me. Okay? It says, here's the trend of the points. Okay? Miraculously, these points are all on the line. That almost never happens. Okay, you almost always have dots that are above and below the line. Okay, and that's okay. The line will always be the trend or the average of those points. All right, now that I've got that, as soon as I clicked on that, I got a bunch of other options show up underneath. Okay, those other options are the type of line. We're always going to use linear, okay? But once in a while, you might, in other classes, you might need some of these other ones. But we're dealing with linear here, so we're just going to leave it, okay, as linear. Whoa. Skipped way down. Okay, so linear, okay? This stuff here we don't generally change. Okay, but here in the label box, I do need to put a label on the line. Oh, I should have put the arrow bars on. I didn't want those. There we go. Okay. All right, so down here for label, okay, we click where it says none, but we want it to show the equation. So if we click on use equation, okay, it'll put up here this little legend or whatever, okay? And it just goes 0.15 times x plus 5. Okay? Everybody's graph look like that. All right, now I'm going to show you what we can calculate using that graph. Okay, obviously we can read from that graph that the more pages you put in the book, the thicker it gets. Okay, cool. Okay, but here's some of the other things that that graph, now that we have the equation, tells us. Okay, this number here is the slope of the line. Okay, so when we got that graph, okay, it looked like this, right? Okay, that number right there is the slope. Okay, so this equation right here is this equation. It is the equation for the line. Okay, it's y equals mx plus b for that graph. So what it's saying is y equals 0.15 times x, so 1.15 times x plus 5. Okay, what do the different parts of that formula represent? If you're in math, you probably recently think this. Sorry, hands up again. How many people have taken this in math already? Okay, so you all know what these parts mean then, hopefully. Okay, y is the y value of any point on the line. Okay, so if I'm looking at like this point right here, okay, it would be, oh, that's a terrible version of that graph. Let's go back to this one. Oh, it did the same thing. Okay, so what it's showing here is that if I had this point right here, okay, and I went across, its value would be 8. That would be its y value. Its x value would be 30, or would be 20. Okay, everyone with me on that? Okay, and then, or sorry, this would be 8, this would be 20, sorry, I'm in the wrong place. This one here would be 9.5 and 30. So y would be 9.5, x would be 30. Okay, so that's what those parts mean. Okay, this number here is m. Okay, m is the slope of the line. It tells us how much y goes up as a function of x. Okay, now in this case, that would be how many millimeters per what? Per sheet. The slope tells me in this case the thickness of one page. Okay, every page I add makes the book 0.15 millimeters thicker. Okay, that's what that slope tells me. Every graph that has a linear function like this has a slope, and that slope tells us something different. On this graph, it's the thickness of the sheet. On a position versus time graph, it's velocity. Okay, on a velocity versus time graph, it's acceleration. Okay, you can figure all of these things out simply by looking at the graph. Yeah. Okay, what did I do here to figure out what it represented? I looked at the units for thickness, and I looked at my units here. And I know that the slope is how much this goes up over this. Millimeters over sheets. Millimeters per sheet. Okay, it tells me the thickness of one page in that book. All right, now, x, as we said before, is the x value of any point. So if I'm looking at this point here, the y value is 9.5, the x value is 30. Okay, this is b. What does b represent? B is the graph's y-intercept, right? It's the value of y when x is 0. So this tells me that the book is 5 millimeters thick when it has no sheets. What does that number tell me? That's the thickness of the cover. Right? If the book is 5 millimeters thick when it has no pages, the cover is 5 millimeters thick. Right? If the graph is telling me the book is still 5 meters thick, or 5 millimeters thick, not 5 meters thick, 5 millimeters thick, okay, when it doesn't have any pages, that must be how thick the cover is, because that's all it would be there. Okay? You see how much we can interpolate or interpret from a graph? Okay, when we have that equation on there, that's what we learn to do in Science 10. Okay, we learn to take a graph and appreciate it and use it for more than just, oh, okay, I get it. Okay, I can actually calculate things beyond the graph or that aren't directly communicated by the graph. Okay, all right, so let's walk through how we would answer these questions here. Okay, so we're going to use this equation to answer these three questions. All right, I want to calculate the number of sheets in a book that is 80 millimeters thick. All right, now, number of sheets is on which axis? X. So they want me to calculate X. And they tell me the book is 80 millimeters thick. What axis is millimeters on? Y. So they told me Y equals 80. Calculate X. Well, I can do that because I know what M and B are. I have 3 out of the 4 parts of that equation. So all I have to do is manipulate to solve for X, the number of sheets. Okay, so to solve for number 1, guys, make sure you're kind of writing this down as we go here. Okay, so Y equals M times X plus B. I know I'm solving for an X value here because number of sheets is on the X-axis and it's the number I don't have. So I need to get X by itself. What should I move first? B. Okay, right now I'm adding B, so to move B, I? Right. Okay, Y minus B equals M times X. I want to get X by itself. What do I do with M? Divide, because right now I'm multiplying it. Okay, so I have Y, it's 80 millimeters. I have B, it's 5 millimeters. And I have M, it's 0.15 millimeters per sheet. Okay, so now I can plug those numbers in and solve for X. 80 millimeters minus 5 millimeters divided by 0.15 millimeters per sheet. Okay, if I do that division, will the millimeters cancel? And I'll be left with sheets, which is exactly what I should get. That's what they wanted me to find. Okay. So if I go 80 minus 5, and then divide that by 0.15, okay, that book's got 500 pages. Okay, that is not on the graph. My graph only goes to, what, 100 pages. Okay, but I was able to use the data on the graph to extrapolate. Okay, that's the term we use. I extrapolated from the trend I had to something that wasn't actually measured. Okay, but I could use what I had on the graph to calculate something beyond what the graph had done. Okay, should this trend continue, the book would have 500 pages in it. Okay, everybody all right with that? Okay, that's what Y equals MX plus B is for. Okay, it helps us to calculate data points that aren't on the graph. Okay, I could also ask you something that would have been here but doesn't have a data point. So I could ask you, how thick would a book that has 45 pages be? Well, there's no point there, but I could calculate it using Y equals MX plus B. Okay, that's the purpose of it. We can only measure so much stuff and put it on the graph. Y equals MX plus B helps us calculate things we didn't measure, using things we did measure. Okay, so that was calculating an X value. What does number 2 want? It wants me to calculate a Y value. How do I know that? It wants to know the thickness of a book. Thickness is on the y-axis. All right, I want you to try and do this one. Okay, I want you to calculate the thickness of a book that has 805 pages using this equation. So for number 2, do I have to manipulate the equation at all? Already set up to solve for y, that's what I'm looking for, so all I have to do is plug in the numbers. I already know from the equation, m is 0.15. Okay? They told me the book had 805 pages. That's an x value, so I put that in there. 0.15 times 805, plus the thickness of the cover, 5 millimeters, okay, the y-intercept. 0.15 times 805 plus 5. All right, so that book will be 125.75 millimeters thick. Okay? Guys, I'm never going to ask you to do more than that on a quiz, on a test, on a lab, okay, with graphs. You will have to use y equals mx plus b to calculate things, okay? What we just did there, I wouldn't ask you to do more than that on the analysis for your lab tomorrow. In fact, we'll do a question today that is exactly the analysis for tomorrow.
Is this going to be on the test on Friday?
Graphing is not on Friday's quiz, just v equals d over t. Okay, now, question number 3, the number of millimeters per sheet. Okay, that's what we started with. Okay, where on this graph do I get the number of millimeters per sheet? Because I don't have to do any calculating here. It was the first thing we talked about. Okay, what number tells me y over x? M. Yeah, this is the slope. Okay, the slope tells me how many millimeters there are per sheet. The slope is how much does y go up as x goes over. Okay, that's going to be in millimeters per sheet. So the slope of that line is the thickness of one sheet, 0.15 millimeters. Add a sheet, you added 0.15 millimeters to the thickness of the book. Okay? Guys, I don't know how many times I've put a graph just like this, okay, on a unit exam and asked those 3 questions. Okay? Calculate an x given a y. Calculate a y given an x. Tell me what the slope means. Okay? Those are the 3 most important things that you can get from a linear graph. Okay? All right, let's look at let's look at the rubber band graph, and then we'll go to the multiple run graph. Okay? See what you remember here. I want you to build the graph, just like we built the last one. Okay? Highlight it, insert chart, build it, put the equation for the line on it. Okay? So, how long the rubber band will be if stretched by 15 newtons worth of force. Okay, stretching force is on the x-axis, so they're giving us x. And they're asking us to find how long length is on the y. So to answer question number 1, we don't have to manipulate anything. We just have to plug in our numbers into this equation. Okay, so m is 2. Okay, and in this case, that would be 2 centimeters per newton. Okay, so if we added another newton worth of pulling force, the rubber band would get 2 centimeters longer. Okay, times 15 newtons. So okay, we're gonna get it bigger, plus b, which was 6.5 centimeters. Okay, so if we plug all that in, we got 30, 2 times 15, okay, plus 6 point, I can't believe this. You get 36.5, do that on the calculator. 36.5 centimeters will be the length of the rubber band with 15 newtons worth of force applied to it. 2 times 15 plus 6.5. Okay, everybody all right with number 1?
Isn't it the unit in meters?
I got centimeters here. Does it say meters on the chart?
Yeah.
Oh, okay. Sorry, I just went with what I had there, guys. That's a big rubber band. That's more of a bungee cord if it's that big. I trust you guys. Oh, yeah, yeah, okay. That's a bungee cord then, a really long one. We're doing this out in the field, this experiment. I probably changed it because that unit didn't make sense. Okay, either way, you got meters, I got centimeters, we have different units on the graph. Okay, what force is needed to stretch the band to a length? I've got meters up there, 18.7 meters. Okay, so what did they give me there? Y or X? They gave me Y, they want me to calculate force. Force is on the X-axis, so we got to take our Y equals M times X plus B, okay, and we've got to manipulate now for X. So subtract B, okay, divide by M, and we've got X by itself. All right, so that's going to mean we take the Y they gave us, 18.7, we subtract B, which was 6.5, and then we divide that by 2. So 18.7 minus 6.5, okay, divided by 2. All right, so we will need to use 6.1 newtons worth of force. Okay. Everybody all right with that? All right. Now, how much calculation does number 3 require? None. That's going to happen. Lots of times on a question about graphing, there will be a question that requires no calculating. Okay? Those are often the hardest ones. Not because of the math, but because they require a certain level of understanding about the setup of a graph. Okay? So here's what I mean by that. How long is the rubber band when it's not stretched? Okay, how many newtons worth of force, or how much force are you applying if you're not stretching it? 0. Okay, so really what they're looking for here is, what's the value of Y when X is 0? They're looking for the Y-intercept, which is how much? 6.5. Okay, you wouldn't believe how much calculating people will do to try to solve that problem. If they're doing calculating, it's because they don't understand what was asked. They don't understand how a graph is built. Okay? So lots of graphing skills and interpretation skills are just around simple things like that. Okay? Another question I could have asked on there that would be a 1-mark question that would require 0 calculating, okay, would be how much force would be required to stretch the rubber band 1 centimeter, okay, or 1 meter? That'd be the slope. It absolutely would be. Meters per newton, that would be the slope of the line. Wouldn't require any calculating, it's right there, it's 2. I'd have to require 2 newtons of force for 1 more meter. Okay, so you really have to look at the question and go, okay, in a question like that, like for this one here, were you even given any numbers? Okay, always a kind of a red flag. If you weren't given any numbers, the answer's probably right in front of you. Okay, these ones gave you numbers. They probably have to use that number. Okay? All right, let's look at the multiple run graph. Okay, this is going to be what we're doing tomorrow in our lab. Okay. All right, so on this one, time is going to be our manipulated variable. All right, and it's our manipulated variable because as the experimenter, I determine how long the object is allowed to move for. Okay, so in that way I'm manipulating the length of the experiment, so time is manipulated. Okay, the positions of 3 different carts are being recorded. So the position of the cart will be the responding variable. Okay, is how I build the graph any different? Nope, it's just going to have 3 different lines on it, that's all. All right, so let's build the graph real quick here. You can do it on your computer at the same time as me here. Okay, so highlight all the data, insert, chart. Okay, oh, look what it did. Google often gets confused when you have more than one data set. So here's how we fix this. Okay, is everybody to this point where it's got the stupid bar graph? Okay, so here's what we need to do. Okay, we need to go to setup, and right here at the top, oh sorry, no, customize. Nope, setup, come on, where is it? There we go. Chart type. Okay, in setup, right at the top it says column chart. We don't want a column chart. We want a scatter plot. So we're going to scroll down. Scatter plot's actually quite a ways down. Okay, right underneath the pie graphs. Just click on that. Now I've got a scatter plot of my data. Okay, and each run got a different color. Okay, so they're easy to tell apart. Now I can go to customize and do the same thing we did for the other graphs. I need trend lines, I need equations for the lines. Okay, so I'm going to go to series. Okay, and I'm going to go apply to all series. Yep, that's good. Okay, I like making the points a little smaller. Okay, and then I'm going to go down to trend line. Boom. And I'm going to go to label and put in use equation. Okay. What's missing from my graph? A y-axis label with units. Okay, there's no y-axis label. There are no units on the y-axis. All right, so what we got to do here, okay, is go back up to chart axis and titles and put that in. Okay, see, vertical axis title, and it's blank. So I just click in here where it says title text, or okay, you could click over here and it would put it in as well. Okay, and I'm just going to put position in meters. Okay, is that a very good title? No. So I'm just going to go here to chart title, where it has all of that stuff, and I'm just going to go. Whoop. Okay. Graph is set up right. I know, I do that kind of fast. Okay? You'll get that fast. Be thankful. 10 years ago, you'd be drawing this out on a piece of paper by hand. This like one unit, one lab would take all period to do the data. Okay? Now you can get a graph in 30 seconds. Okay, now a couple of things that are weird on this graph. One of the numbers is in scientific notation. Okay, you see that one that says 9.52 e negative 3? Okay, that's, okay, a number in scientific notation means this, guys. Okay, so that number right there, 9.52 times 10 to the minus 3 means we wrote this number like this because we moved the decimal 3 places to the right from where it was. Okay, this means this number is actually really small. If this was 9.52 times 10 to the positive 3, it would be really, really big. Okay, it would be 9,520. Okay, but in this case, it's 0.00952. Here's how you can do it if you're ever lost. Okay, if I have 9.52 times 10 to the minus 3, if it's minus, I'm going to move the decimal this way. 1, 2, 3 spots. Okay, so that means there's the decimal now, 0.00952. Okay, that's the actual number. All right, and the same is true if it was 9.52 times 10 to the positive 3. Okay, then I would go 1, 2, 3, empty cups get zeros. 9,520. Okay, everybody all right with that? Your math teacher won't like that I did that. But that's how it works. All right. First question on here. What's the velocity of each cart? What are some units that we use for velocity? Meters per second. That's the most common one. Are those units both on this graph? Meters is on the y, seconds is on the x. Okay, now this is a graph that's telling me where the objects are as a function of time. So would dividing the position by the time give me meters per second? It would. So would the slope of the line also have units of meters per second? Okay, so for question number 1, do you have to do any calculating? What's the slope for cart 1? 1.38 meters per second. There's your velocities. On this graph, okay, the slope of the line is telling me how fast the object is going, because it's telling me how many meters it goes every second. Okay, that's not something you need to memorize. Every graph, you can do exactly what we just did. We look at the graph and we go, okay, this graph tells me where the object is. It tells me how long it takes it to get there. How far and how long divided by each other are how fast. Okay, perfect. The slope of this line is velocity. Done. Okay, you can do that for any graph. It's an analytical skill that we want you to build. Okay, because in Science 10, we're only going to do 2 graphs. You could probably memorize everything, but I've still seen people mess it up. Okay, but by the time you get to Physics 20, Physics 30, Chem 30, or Chem 20, Chem 30, you're going to have 24 graphs in each course. Okay, if you're trying to memorize everything off of 24 graphs in each course, so that's almost 50 graphs, you're cooked. You're never going to memorize that correctly. Okay, you're better off to have this one skill, this one analytical skill, that will ask you, or that will allow you to do that. Now, what's on here, okay, these 3 questions, is exactly what we're going to be doing tomorrow with our lab. All right? So, we got a little bit of time here. Instead of each cart, I want you to calculate for me the position of cart 3 and, position of cart 3 and how long it'll take cart 3 to go 50 meters. Okay, so position of cart 3 at 12 seconds, okay, and how long it'll take each cart to go 50 meters. Or sorry, just cart 3, so the yellow line. Okay, so do that just for the yellow line, 2 and 3 for the yellow line. Okay, so I'm solving for y, I'm given x. X is 12 seconds. Okay, so y equals, for cart 3, 3.39 times 12 plus 0.0381, okay, punch that in and you've got your position, okay, after 12 seconds, so 3.39 times 12 plus 0.038, 381. Okay, so we should get a position of 40.72 meters, okay? And then for x, how long will it take? Sorry, for number 3, that is x, how long will it take? Y minus b over m. Okay, 50 meters minus 0.0381, right, divided by m, which was 3.39. Now, here's where you have to be careful. You have to do the top before you do the bottom. That means you have to press enter. Okay, you have to go 50 minus 0.0381, enter, okay, and then divide that by 3.39. If you don't do that, okay, it's not going to come out right. Right, so you get 14.7 seconds. All right, questions there? All right, please just sign out of your Chromebook and leave it on your desk. Okay, my favorite 2 class needs them, so okay, there's no sense putting them back in the cart. Okay, just leave them on your desk, please.